good morning. Today I'm feeling better. So today will be the, yesterday I talked a lot about API, PGAS, and InfiniBand, high-speed networks. But today's focus will be the other aspect, which is upcoming, is mostly with the Hadoop and Memcached and big data. So probably if you see, the big data, there is a lot of discussion these days in the community, both HPC community, networking community. So it basically provides a groundbreaking opportunities for enterprise information management and decision making. And if you read a lot of literature, like people are indicating that the rate of information growth appears to be exceeding even Moore's law. Every day more and more data is being added and people are trying to make decisions on those data. So you need to actually analyze the process and analyze the data in the best possible time. And there is some literature here saying if just by the end of this decade, like 35 zettabytes of data will be generated, and there has to be capability to process all this data. Now this is a chart which is just showing like just the word big data. I mean, that is so frequently being used. It's a very nice capture from Twitter, just within over a period of 8 hours and 24 minutes. This is like trying to show how the users are using the word big data, okay? And that comes from all different domains, like it might be big data analytics, big data cloud, even big data jobs, big data social media. So all different kinds of groupings are taking place, and then people are exchanging information just in 8 hours. This kind of information is being spread. So yesterday I showed like how the top 500 systems are evolving, and especially on those top 500 systems, the clusters are making a big impact. And now if you take a look at this, for the same big data kind of environment, if we want to use the clusters, now the modern networking technologies are coming, and this is the charts taken from the top 500 systems again, saying what is happening with the interconnection networks over the years. Some of you might have seen it. So here is the chart, like starting from like 1995 to 2012, the November ranking. And the left hand side, it shows the interconnect families system share. That means out of those 500 systems, how many systems are using network X versus network Y versus network G. And then the right hand side, it is trying to show the performance share. It is not just the absolute number, but out of all those systems, like the top 500 systems, if you compute together their performance, like each network, network X is contributing to how much performance versus network Y versus network G. So there are two different metrics. So here if you see, of course there is in the earlier days, there used to be a lot of these kind of the Myrinet, Quadrix, kind of SP switch, those were there. And this is the time frame, like the 2001, the InfiniBand started coming. So this is the yellow line, and this is the Ethernet. So here if you see that over the years Ethernet has been there, and this is the yellow one, which is the InfiniBand started expanding in the 2005-06 kind of time frame. And this is in the terms of the numbers, but if you see the performance wise, there is a big difference. So here you will see that this is like the InfiniBand is contributing to a lot of significant fraction in the performance. But there are also the other ones, like this is one, like the custom interconnect, most of the Blue Gene, Cray, even the K supercomputer. So all those systems also contribute. Now for this discussion, today's talk, we'll try to focus on the commodity side. So that means InfiniBand and Ethernet and all the different versions. Okay? And trying to see for this kind of networks, and if we want to design systems to process Hadoop, so how exactly we go about it, and then how we want to design the systems, and which systems will be able to deliver the best performance. So that will be the objective here. So let's take an overall look at the HPC side, what is happening. And as we know, like HPC has adopted advanced interconnect protocols, not only InfiniBand. There have been like 10 gigabit Ethernet, or the IWARP has been there. And also there is this RDMA over converged enhanced Ethernet, which is called ROCKY. That is also getting into the mainstream. So it basically uses the RDMA software, which is like the IB stack kind of things, but the actual hardware is Ethernet, like the switches and all are Ethernet. So that is a combination of InfiniBand and Ethernet. And these networks and protocols are providing very good performance. I mean, these days you can get few microseconds. InfiniBand gives, I showed yesterday a number like 1 microsecond. iWork is giving around 5 microseconds. Rocky is giving around 3 microseconds. So you get in the ballpark of 1 to 5 microseconds. And bandwidth, especially with InfiniBand dual FDR, nowadays we can get 100 gigabits per second. And of course, all these networks also provide very low CPU overhead. And that is important. A lot of people ignore this aspect. This is the third metric, because when you are trying to do some basic evaluation of network, you can say, yeah, I can give you the best latency and mesh bandwidth. But then if you ask the question, what percentage of your CPU cycles you are utilizing to deliver that performance, the answers may differ. So might be there is a network or protocol can give you the very good bandwidth, but it will try to utilize 90% of your CPU cycles. So that means only 10% is left for your computation. So you cannot see that when you just do the naive benchmarking, but when you put the application on top of it, then you see the difference. So that's why this is also important, that any network and protocol should give you the low CPU. And in this ecosystem, I'm sure many of you know those Open Fabrics, that is the organization. How many of you know Open Fabrics? Some of you. This is the which used to be known as the Open InfiniBand many years back. And then that took also the Ethernet also into account, so both iWork, Ethernet, Rocky. So everything now falls into this Open Fabrics environment, and then there are unified stacks, and that is the stack which is being developed over the last 12 years, and most of the systems, vendors, they use that stack to basically, whether you have an InfiniBand deployment or iWork deployment or a Rocky deployment, that is the stack that's used. And that is the kind of stack is actually driving a lot of these top 500 systems. Now, over the years, so what has happened, as we saw yesterday in my talk and as well as also from the community, of course these days all the message passing interface, MPI stacks, all different vendors and all, they have already moved to InfiniBand, the low level verbs or the iWork verbs. Similarly, parallel file systems, there are a lot of file systems these days, they are trying to take advantage of all these, the best performance from these networks. Same thing is happening with the storage systems. Now almost like if you take a look here, 12 years of research and development have already gone in terms of the HPC system since InfiniBand was introduced in October 2000. And also not only these MPI, but other programming models are emerging. I gave an overview of UPC, OpenSPAN, hybrid, MPI, PGAS, OpenSPAN. So all those are also emerging. Okay. But then what is happening is the other community which is just coming out now. Okay, so overall I'll show you towards the end of this talk, it's like a history repeating itself. Okay, whatever we saw 12 years back when InfiniBand was coming, there are a lot of studies, discussion, and saying, okay, the competitors were Marinette and Quadrix. I don't know how many people know that kind of a time period. In like 2000, have you seen a lot of studies between InfiniBand, Marinette, Quadrix, kind of thing? Anybody familiar? No? Okay. So there were a lot of these studies, and then people were saying, no, this network is not good, that is not good. So people didn't know how exactly to do the studies. Okay, and that's what we'll see. I'll show you a lot of numbers, and especially that's what is happening in this big data community. People are not properly doing the benchmarking or not properly analyzing where the bottlenecks lie, and that leads to all different kinds of conclusions. Today you will read saying, yeah, that network is best. Tomorrow somebody else will say, no, that is not good. This network is best. This protocol is best. So that's what is happening, but none of these studies are being done in the correct manner. So especially here in the big data thing, the two things I'll try to focus. One is of course Hadoop, and I'm sure many of you know about this. So Hadoop has a lot of different components. I'll go over it. And also there's a Memcached, which was indicated yesterday in the RAM Cloud talk. That is also like a part of the Web 2 infrastructure. So I'll try to focus on these two components and see what are the challenges there and how you can accelerate those using the advanced methods. So the broad challenges here is that can high-performance interconnects benefit enterprise computing? So that's the broad goal. So of course, most of the current enterprise systems use 1 GB, and not only it is a 1 GB, they also use the sockets, and sockets means TCP/IP. So that's what is being used. And that leads to some concerns for performance and scalability. You can deliver some performance for some kind of applications or some range of systems, but as soon as you start growing, you might not be able to get the best performance or scalability. So then, as we saw, like the high performance networks have been actually influencing a lot of these top 500 systems. So that has generated a lot of interest from Oracle, IBM, Google. So they are already working in their directions. Like if you see some of their Oracle, their database servers, IBM database servers, so they already have like products with InfiniBand and all, not only local area, wide area, very integrated kind of things. So the question here are that what are the challenges? Okay. And then where do the bottlenecks lie? And that's what I'll be trying to show some numbers, because once we are talking about big data, it is not just the CPU and the network. Now the storage also you need to take into account. Okay, because the data resides on this storage, and then the storage means again it's a hard disk drive or it's SSDs, so all kinds of variations are there. So we need to put them together and see what works and what doesn't work. So these bottlenecks we eliminated with new designs, so similar to the designs adopted for API. Okay. So we started this research around 2 years back. IBM gave us some seed funding saying, okay, you people have done a lot of work on API, so why don't you start investigating some of these issues, especially on the big data Hadoop environment. What can high performance networks benefit? Okay. Can they really benefit, or what will be the limitations? So that's how we started, and I'll be trying to show some results along those directions. So the talk will be presented like this. First, I'll try to go a little bit overview of the Hadoop. That means there are different components, HDFS, MapReduce, Hbase. So those are the bigger components inside Hadoop. I'll introduce them, and I'll also introduce Memcached. Then I'll talk about some of the challenges in accelerating this enterprise middleware, all these different components. And then I'll try to show some designs and case studies. First I'll start with Hadoop. We'll go over the HDFS, then MapReduce, then Hbase, then some combinations of this, because these are different components. Some component can run with InfiniBand, some component can still run with sockets. Now if two components we take and then put them over InfiniBand, do we get even better benefits? Okay, so those are the kind of numbers we'll be showing. And then I'll show some Memcached, and then I'll come. So this is the broad Hadoop excuse me. The picture, it is basically an open source implementation of the MapReduce framework. So that is the kind of a programming model. Yesterday we heard from Yale Goodkin yesterday. He gave an overview of the MapReduce framework. So basically when you have big amount of data, you try to have a set of mappers which are trying to divide the data sets, and they're trying to do some processing and then sending it to the reducers who are trying to merge all these data and then giving you the solution. So that is the kind of like a MapReduce framework. And broadly what happens is, so in this, this is the Apache Hadoop design kind of thing. So it includes the MapReduce, HDFS, and also Hbase. And here is the underlying is the Hadoop distributed file system, HDFS. So this is not like a Lustre or GPFS, which we use typically in the HPC side. So this is the HDFS, which has been designed, and I'll introduce that in the next slide. Which is the main file system. On top of that, we have these different components, and then you write the applications, whether it's a MapReduce kind of environment or Hbase oriented applications you write. And this model, people have shown that it scales, but at the same time, it also leads to a high amount of communication. And that means, that's what we'll be trying to show later on, that has potential for using the high performance networks, and then trying to improve the systems, and then cutting down the time or the execution. So this is the Hadoop distributed file system, or HDFS. So this is the primary storage, as I mentioned, and since it comes from the enterprise world, the HDFS has been designed to be reliable and fault tolerant. So what happens is, for every data you write, there is some typical degrees of replication you can specify. The default is 3. So that means every data is actually, there are 3 copies in the system. Okay. So if a node dies, you can still recover and then continue. Okay. So it is unlike our typical HPC, Lustre, GPFS and all. So there we don't take this kind of reliability and fault tolerance already to the file system, whereas here it is already built in. So here you can say like these are the set of data nodes, and then there is a name node, then there is a client, and there is also another component called Zookeeper, which keeps track of a lot of things. And this environment has been adopted by many organizations, like many times you might have seen Facebook uses the Hadoop, HDFS and all kinds of things in their environment, even Yahoo uses. So this name node actually stores the file system namespace. So that means which data is residing on which of the data nodes, and the data nodes actually stores the data block. And this entire framework has been developed in Java for platform independence and portability. So that is good thing, but the bad thing is, if some of you know the Java and have used Java, it's not good for extracting performance. Okay, the Java is a very heavy code, so getting performance is very tough. But at the same time, it provides very good portability across different platforms. And also, like, since these environments were all designed many years back for commodity low-end systems like the 1 gig kind of environment, so they have been using the sockets for communication. So here, if you abstract it up and then try to see, okay, what happens in the network level, and that's what we'll be focusing here. So you will see like this. So there are a set of clients, and then there are a set of data nodes. These are the HDFS data nodes, and they can have one or multiple of hard disk drive or SSDs. Okay, and there is a high performance network which is connecting. So all the HDFS operations will see that this is going over the network. Different clients are trying to access to the HDFS. So this is where we want to see whether we can accelerate the network components. Okay, so and how much benefit it will try to give it to the upper layer in the applications. So then the second component is the Hbase. So this is the database component of the Hadoop framework. So it basically, like, there is an Apache Hadoop database. You can get more information here. It is a semi-structured database. Again, the original design is to make it more scalable. And this is again also an integral part of many data center applications, like the Facebook social inbox uses this Hbase component to provide support to their own large number of users. So the way it looks like, the architecture is that we talked about HDFS. So but within Hbase, again, they have, like, there is the Hbase master, there are some different Hbase region servers, and then there are Hbase clients, and they are all connected with this duty. So this also, since it is a part of the Hadoop framework, again it uses the Java for performance and independence and portability, and it also uses the sockets for communication. So from a network perspective, so this is how it will look like, and we'll again bring back this later on. So this has two levels of network involvement. So the first one is, of course, like the Hbase clients are talking with the H region servers. So there could be one or many of here, and they are communicating over the networks, and the H region servers are talking to the HDFS here, and that also is over the network. So we'll see two levels of interaction with the networks. So the other one is the Memcached, and this is coming from a little bit different environment, like the RAM cloud and all, to store the data in memory across a lot of nodes. Okay. So here the objective is that if you take any multi-tier data centers, so you can have, like, the front end servers are like this, which are the Memcached clients. So this could be like Memcached servers. These are the database servers, and they are connected with high performance networks. So broadly, what we are trying to do is we are taking some part of the main memory of all these nodes and trying to aggregate. Okay, so that's the whole broad design of the Memcached. You can just purely take the memory, or also you can take the memory plus also some parts of your SSDs. That is the next generation design which is being worked out. And basically it tries to provide a distributed caching layer. Okay, so think of, like, let's say you have 100 of these nodes, and each node is contributing like 16 gigabytes of memory. So you have 1,000 nodes, so 16,000 gigabytes of memory, where you can put a lot of hot data. Okay, and this is where your query processing and all becomes much more faster. And this it is a general purpose, but you can typically use to cache database queries, the results of the API calls, so that when the newer queries are coming, if the data is already there in the Memcached layer, you just grab it from there and give it. Okay. You don't have to really go to the storage or file systems, and so that you don't get slowed down. So that's the whole idea. And then this is an integral part of the Web 2.0 architecture. So any system which is using Web 2.0 environment actually uses Memcached. And this is again a scalable model, but based on like how you are trying to do this query, whether it's a shorter query or longer query, you will see like it could be also very network intensive. So the challenge again here is that can we take the high performance network and try to alleviate this or try to accelerate these operations so that the entire environment can be more, deliver high performance and be more scalable. So now with this kind of a background, any questions on these backgrounds? Is everybody clear the architectures and all? Okay. So then the question is, okay, what are the challenges in accelerating these components? So here it is a figure similar to what I showed yesterday. If you remember, those who were there in the talk, I showed like especially from MPI, PGAS perspective, how you try to design the software stack. And here it is no different. Okay, only some minor differences will be there. So here if we see, there are like commodity computing systems these days are coming, multi-core, many-core architectures and accelerators are coming, all these different kinds of networking technologies, InfiniBand, 1 gig, 10 gig, 40 gig, RNICs, intelligent NICs. And also the bigger thing is to the equation is now storage technologies we need to take into account. Because we are talking big data, data has to reside in some storage, so they play a very important role. Okay. So later on when we show some performance numbers and all, we'll see there will be very interesting interplay of networks and also the storage technology. So then from the top we have the applications, and then the application is written with some middleware. This could be like HDFS, Hbase, MapReduce or Memcached, and then there is a programming. So currently it is sockets, but if we can change that to some other model, we'll see that whether we can use the InfiniBand verbs or some other protocol. So then we might be able to get better performance there. And what happens here, this is the communication and I/O library. Okay. So basically we need to take the performance here or the features here and then try to design these components and then pass it to this layer so that the application can take it. So the broad challenges again will be like how do we do best point-to-point communication. Of course in this environment we don't have collective communication like what we discussed yesterday, like a lot of collectives, broadcast, radios, all these, they don't exist here, so we don't have to focus on that. But we also have to focus on I/O file systems, threading models, different kinds of synchronizations, quality of service and fault tolerance. Okay. So the problems are very similar. Now, of course, since this field is just evolving, I'll just focus on only point-to-point and some parts of I/O and file system. So this is we just started this research only 2 years back, so all the things have not been explored. Hopefully over the years, we'll be trying to show all the kinds of interplay. But for the time being, we'll only show these two things. But more importantly, what I want to give a message towards the end is that it is not just this layer. If you see, there is always like any time you design a software stack, there is an interplay, okay, across all the different layers, okay. And what has happened is, like, for the time being, what we have assumed is like, if we have, let's say, we do a partition here, we don't change anything in the upper layer, okay. We just changes or make enhancements to the lower layer, only the communication and I/O, and try to see the benefits. But the problem is more complicated because these stacks have been designed with slow networks in mind. So now if you just make the network component more efficient, you get some benefits, but that's not just the end of the story. You need to go to the upper layers and see that, can I change the algorithms, can I change the data structure, can I change the way these stacks have been designed so that we can get additional benefits, okay. And that I think gradually will come over the years, and we have not even touched that part at all, okay. And that gives to, if some of you people have been in the HPC field for many years, especially like around 10 to 15 years back, a lot of people were saying, when people were trying to find out what support we need to provide in the network to accelerate collectives. Okay. So then some people will go and look at the code saying, okay, see what people are using. Are they really using collectives? Then some people came up with an answer saying no. Okay. So then you can argue saying, oh, nobody is using collectives, so why should I provide the support for collectives? But the real answer was that on those older generation machines, since the collectives were so slow, the application programmer didn't want to use the collectives. They tried to use point-to-point communications to implement collectives. Are you seeing the difference? So it is a chicken and egg problem. So if the underlying system environment doesn't provide you good support, then the application programmers don't use the primitives. And you cannot use that argument to say that, oh, that is not needed. Okay. So once you provide then all the modern systems, when the collectives got enhanced, the collective algorithms got enhanced, and the libraries try to provide good collective support, all modern applications, they use collectives. Okay. So that's exactly is happening like here. So many times you will see that people have written this kind of upper layer functions and all, assuming that the network is slow. And now if you want to accelerate this, after that we need to revisit this so that we get the benefits from both sides, and then that will be the best system. So now let's come to this open fabric stack I introduced here. This is a very dense chart, but it summarizes of all kinds of interconnection protocols, what is happening in the community. So broadly, if you take an application here, there are two kinds of paradigms now. Either you go through the sockets, or you go through a modification which has been written using verbs, which is like the InfiniBand introduced, and also the iWarp also introduces. Okay. So the difference is that either you modify your applications or a middleware or not. Okay, so that's the two broad categories. Then within that, there are different kinds of sockets-based design. Okay, so either this is like the traditional, like the kernel space, you have the TCP/IP going to Ethernet adapter, Ethernet switch. So these are the traditional 1 gig, 10 gig, 40 gig products you see. Or you go through like even the InfiniBand provides a emulation of TCP/IP that is called IP over IB. So it's the same sockets application, it can run over InfiniBand, but it just goes through the TCP/IP emulation. It's not the best performance, but you can still have the portability so that you can write your applications. And then these are like the hardware offload, where you have the TCP/IP being enhanced, which is called the TOE, and that goes through the Ethernet adapter, Ethernet switch. So these are the kind of the traditional sockets. So these are like the Chelsea's product or Detect product kind of things where they have the TOE inputs. Then on the extreme, so in the intermediate one, this has been there for some time. It's called a sockets direct protocol. So this Mellanox introduced, Mellanox and Microsoft, but it's gradually phasing out. So it tries to accelerate the sockets with some RDMA semantics of the InfiniBand, and this runs with InfiniBand adapter, InfiniBand switch. So we'll say that this is the SDP stack. So then in the rightmost is actually the highest performance and the maximum scalable, which is called the basic InfiniBand, which uses the RDMA. But here the stack has to be rewritten using these verbs. Okay. The stack means if it is an API stack, or if it is a file system stack, or a PGAS stack. So all these things you need to rewrite with the verbs so that you get the maximum performance. Okay. Again, your end application will need not be modified. For example, if you are an MPI application, if the MPI library provides this, then your job just runs. Okay. So it has to be at some level of middleware or application, you need to make the change. And as I mentioned in some of the earlier slides, over the last 12 years, a lot of middleware and applications have moved to this side already from the HPC domain. Of course, the big data thing has not moved, and that's what I'll be trying to show some results here. And then the next one, which is coming recently, there is a newer effort which is going on, being initiated by Intel and some of the other organizations called R-sockets, called RDMA-enabled sockets. So it still again provides a socket semantics, but it goes over the user space, provides InfiniBand adapter, InfiniBand switch, called R-sockets. And then two intermediate ones here, I think just for completeness. So this is where the iWarp sits. So it still also uses the verbs. It goes through the user space, and this is the iWarp adapter and Ethernet switch. So that's the kind of the Chelsea's product lines, and the older net effect which has been acquired by Intel. And then finally, this is the convergence, which I have been mentioning, the ROCE, the RDMA over converged enhanced Ethernet. So what it basically is the same verbs layer. If you see whether you use iWarp or IB, but it goes through the ROCE adapter, and ROCE adapter is no different than InfiniBand adapter, but it's just a modification of the firmware, whatever Mellanox sells. So you get the same adapter, but with a little bit modified version of your firmware. But the difference is that it can run with Ethernet switches. Okay, so you don't have to go through the InfiniBand fabric, you can go through the Ethernet fabric, and this is the kind of the ROCE. So this actually comprises of all the interconnects and protocols which are available in the commodity world these days. So what I'll be trying to focus, most of the people try to show here, but I'll try to show whether people can move here, the big data applications and environments can move here, and if so, what will be the benefits? What are the challenges, and then what will be the benefits? questions so far? Everybody's in sync, awake? Okay. So if you take a question saying that, okay, can big data processing systems be designed with high performance networks and protocols? So the current design, most of the designs are like this. I'm trying to abstract from that bigger picture to a smaller environment, like saying applications are written with sockets, they are running with 1 or 10 GB network. Now there are different kinds of products which are coming out called accelerated sockets. Different vendors have, saying they have big data accelerator, they have HDFS accelerator, X accelerator, Y accelerator. So broadly what they are trying to do is provide some kind of an accelerated sockets here, and then that can work with words or hardware offload. But the broad challenge here is that these are still using socket semantics. You can accelerate it, but still the application has not been modified, or the lower part of the application has not been modified. They are running with sockets. And basically, as many of you know, the sockets are not designed for high performance, and especially the stream semantics of the sockets have mismatched for the upper layers for these big data components, and also like zero copy is not available for non-blocking sockets. So even though you accelerate, you go up to a certain extent, you cannot totally bridge the gap or try to extract the performance, what people call like a bare metal performance. You cannot get it. So what we ask the question, saying that just like what we have done for the MPI and recently for the PGAS over the last 12 years, can we take a lot of our knowledge and design into this kind of an environment, saying, considering earlier we were considering these are like MPI middleware, but now we can consider it as a big data middleware. Can we have some kind of newer design so that they can actually directly use the verbs interface? Okay, and if it can use the verbs interface, so then we can run it over InfiniBand, we can run it over iWork, we can run it over Rocky, all the verbs pictures, whatever I showed in the previous slide, all those environments can take advantage of it. Okay, and if you can enhance these components like HDFS, MapReduce, Hbase, Memcached, then your end applications, they don't need to be rewritten. They can actually take advantage of our middleware and then try to extract the performance and portability. So that is our goal. But interestingly, as I indicated, it's not just the network matters, but here since we are talking about the big data, the storage also makes a big impact. And most of the current generation enterprise systems use the traditional hard disks. Okay, so and as most of us know, like since the hard disks are slower, so the high performance communication protocols may not have impact. Okay, and this is kind of a confusion which is still there in the community. And I can give a very nice example. Let's say you have a old car. Think of very old car. Okay, it has like your old tires and all, and then you say, oh, I'll go and replace this engine. Will it run faster? Answer is no, right? The bottleneck lies in the tires. Okay, so you need to replace the tires and the engine to make the car go faster. So same thing is happening here. So a lot of studies people try to show, saying no, I provided an InfiniBand network, it is delivering the same as 1 gig. I'll actually show some numbers. That is true. But then you need to see where is the bottleneck. Is it the hard disk is the bottleneck, or the software stack itself is the bottleneck? Okay. So unless you do a very detailed analysis saying where the bottleneck lies, you cannot just say, okay, I am replacing this with X and I don't get the performance. And that may not be your correct interpretation or correct answer. So that's what we'll see. So the SSDs and other storage technologies are emerging, and does it really change the landscape? And we'll see some very nice results as I showed you. So now let's go into some of the detailed designs and case studies. So I'll start with the HDFS and Hadoop HDFS, then gradually go into MapReduce, Hbase, others. So what we did is, this was the first work we started because in the Hadoop, HDFS is the lowest layer. So we tried to ask the question saying, okay, can we just accelerate that, okay, the HDFS itself. So the HDFS internally, if you see, this is how what happens. The HDFS has write and read. And HDFS write involves the replication. As I mentioned, the Hadoop environment, you can specify replication for every block. It actually makes multiple copies in the systems for reliability and fault tolerance. So this is where actually the data is moving over the network, going to the other nodes, and is being stored. Okay. And the HDFS read is always mostly node local. So that's so we try to focus on the HDFS write. So there is the HDFS write, and in this HDFS write, Of course, there are a lot of algorithms and data structures inside HDFS, and as I indicated earlier, we have not touched those. We just took the write operations, and that is written with typically the Java native interface or JNI. And what we did is, this JNI was earlier talking with like this Java sockets interface was talking with the sockets. Now, instead of that, we try to plug our verbs level design. Okay? So that it can actually sit on top of IB verbs and can run over anything. Okay? Now, that is the part mostly we modified here. Of course, there are a lot of other parts because the Hadoop is a very integrated framework. Okay, you have to establish connections, if the clients have to talk, zookeepers, so all those things we still kept our sockets. Okay, gradually we'll be trying to replace those things. Okay, so we just tried to take the common data part or the HDFS write part, but we kept all these things still on the Java sockets interface so that the middleware can still run. Okay. So whatever numbers I'll be showing you, they deliver performance, but there is much more opportunity there. Okay, we have not optimized the complete stack. Okay. So this is so JNI bridges this layer, bridges the Java-based HDFS with the communication library written in the native code. And as I said, only the communication part of HDFS write is modified. No change to the HDFS architecture or no changes to this. So then this was the paper which was presented at the Supercomputing 2012, just a few months back. So first we tried to see, okay, what is the gain in the communication time? So that means HDFS write, when it is going over the network to make the replication, how much time we are trying to save here. And this is trying to show, and these numbers were taken with 32 nodes, data nodes, and still hard disks were used. On each of the data node there was one hard disk. And it's trying to show here the communication time. So there are 3 bars, so these are like a 1 GB. And then we are using IB, InfiniBand QDR, but the InfiniBand QDR we have 2 of these. One is the IP over IB, so that is the sockets is running there. Okay? Because the HDFS between whatever is running here 1 GB, HDFS, the sockets version, that can also run over the IP over IB version. Okay? So only the underlying network is modified. But this is the new design which is actually taking into the verbs. Okay? And it's trying to show the communication time over different file system size, which is like 1 gig to 5 gig. And here we saw that as almost like just compared to the IP over IB, we get around 30% improvement just in the communication time. So it's the same network. We are changing from the sockets level design, which is the default, to our new design, and in the communication time we get 30%.
Is that dual 1 gig? How do you get?
No, just 1 gig. Just.
How do you do a gigabyte in 5 seconds?
No, this is the communication time.
Okay. It just still seems like it's 200 megabytes a second if I can still know that. For the 1 gig, you will know.
This one?
Yeah. Is that 5 seconds on the left column?
That's true. Little bit lower than the 5 seconds. We can discuss that.
All right.
So then, with the 1 GB, here we get around like a 87% improvement in the communication time, and on these particular nodes we changed to the SSDs, and just for the communication time we saw similar kind of improvements. Okay. But that is just saying this the replication time. Okay, whatever is happening. Now we try to put on some application on top of that. Okay, and this is where like the common thing which is used. Called something a test benchmark called DFS-IO. That is a very common application which many people use. And so here what we did is, so this test DFS-IO we tried to run, and there are 2 different clusters here. So we have a 32 with hard disk and then the 4 with SSDs. Node, we didn't have a lot of SSDs, so we couldn't carry out all the 32 node things. And here again we'll see like this is trying to show the throughput. Okay, the DFS-IO is trying to show the terms of the throughput, and this is like the 1 GB versus the IP over IB QDR, and then this is our new design. And here you will see that, especially on this side, we get around like the over IP over IB for 8 GB file size. Here we see around 13.5%. And with the SSDs, with similar kind of 8 GB, we see a little bit better improvement, like 15%, because now the SSDs are faster, so the data replication is taking place a little bit faster, and so that's why we get a little bit benefit. Yes?
What performance would you expect if you use a comparable Ethernet bandwidth of 10 or 40 gigs?
I mean, that is always the question. We have not done those.
So is it only a bandwidth
No, just wait. I'll show you. There are a lot of interplay takes place there. It's not just the bandwidth. Okay. Then if it is a pure bandwidth, then you can just replace any network and then click it. But it doesn't happen. Okay. Let me finish and I'll come back. So then this is now the question, of course, there is a configuration issue comes. Now many people ask, okay, should I be using one hard disk? Can I use two hard disks there? Will the performance will increase? And this is a very important thing, because when we are talking about the big data, because now we are talking about file system caches there, how much the buffer cache is there, how the data is distributed over hard disk, multiple disks. So we try to do some studies here, and interestingly here what we saw here, like there are this is the average throughput, and this is again the file system size. There are 6 bars here, and 3 of them are with one hard disk, and another one are with 2 hard disks. Okay, and especially since this is a test DFS-IO, and DFS-IO actually uses a MapReduce framework, and that actually leads to saying how you distribute the data on the disks. Okay, so if a system has multiple disks, then multiple mappers, multiple reducers are distributing the data, and that actually brings to the performance. So here we saw, like, these are the 3 things. So this is the 1 GB with hard disk. This is IP over IP with the one hard disk. This is IP over IP so this is the new design with 1, and then these are with the 2 hard disks. Okay, so here we see that around 10% improvement for 10 GB file size with one hard disk, but once we are putting 2 hard disks, exactly the same thing. We are not changing anything. The environment has, instead of 1 hard disk, 2 hard disks, so the data is being distributed over the multiple hard disks, and we see 16% improvement. Okay, so that means again it's just like designing a parallel environment. Okay, as many of us know, like when we are trying to write parallel applications, bottlenecks can lie in all different places, and we need to see where the bottleneck lies and how to alleviate that, whether the application is perfectly balanced, whether the data is distributed. Then only we can study the benefits of it. So here in this study, our conclusion was that if you use like 2 hard disks versus 1 hard disk, like we get for the new design, we get around 2% factor of 2 improvement. Even the IP over IP itself also gives improvement. Okay, and you can get also same benefits with 1 GB also. So it just says like try to provide more disks, and then you will try to, because for the same data size, if you are trying to provide more hard disks, then the traffic or the bottleneck is being dissipated. Okay. So then we try to analyze with the same HDFS design. We try to take the Hbase. So there is a YCSB, which is a common benchmark, a Yahoo cloud service benchmark. And this is how you use for Hbase. So here what was happening, because Hbase is a separate component, I'll show later on our new design of Hbase. But this is the old design of the Hbase, or the default design, which was running over TCP/IP. But we tried to run it with our new HDFS design. Okay, like comparing the old and the new. So here what it says, like this is again 1 GB. We're trying to run the IP over IP, that's the Hbase, and then the HDFS with IP over IP, and then this is the new design. And this is trying to show like a average latency. So this is the typical put latency, and here is the put throughput. So here it is lower is better, it is higher is better. So here we saw like for almost 360K records, for the IP over IP design, let's say it takes 252 microseconds, here we can reduce to 204 microseconds. And similarly kind of Hbase put in terms of throughput, here we get around 3.63 kiloops per second, whereas the new design can give you 4.42 kiloops per second. So we get around 20% improvement in both average latency and throughput. So that was actually the single server and 100% update. So there are different modes in evaluating this YCSB. So then here we try to evaluate with 32 region servers and 100% update. And similar kind of things here we see for around 480K records, 272 microseconds versus 201, or 3.60 kiloops per second to 4.42. So around we see 26% improvement in average latency and 24% improvement in the throughput. Yes.
So I just want to relate the 2 graphs. On the left, I have average latency 300 microseconds, and that's for 120,000 updates or for 1 update?
No. This is the number of records. This is the number of records. So 120,000 records And
so I basically write 120,000 records in, not in 300 microseconds. Each of those 120,000 takes 300 microseconds.
Let me remember what exactly we did here. So it's the records, and then there is a 32 region servers, and there is a mode saying, okay, you have like 50% update or 70% update or 100% update. So
is this, the throughput is like 3 megabytes a second, which is different than this throughput I quite a bit.
which one? Which one you are saying?
Well, doesn't that say?
So this is the throughput kiloops per second.
Oh, kiloops per second.
Kiloops per second.
I can't read, I'm sorry.
Yeah, kiloops per second. Okay.
Great. I get it. Thank you.
Okay. So those are the kind of things just on the HDFS. So then we try to see the similar kinds of design, can we take it to the MapReduce, and the problem is again very similar. Okay, once you handle one component, you can do the other one. So here the thing is, it is for the MapReduce. I think yesterday again from the Goodkin stock, we saw there are different job trackers, task trackers, and a mapper and reducer. So this is what we have tried to do, the RDMA enable, and then try to put our OSU InfiniBand design here, so that just the MapReduce jobs can also take advantage of InfiniBand works. And the way the MapReduce jobs get evaluated, again, there are different kinds of benchmarks. Like we'll start with the very simple one, the sort. That is a very common one, a lot of people use. So here, again, like using the sort, so this is we had two different cluster size. One is like a 4-node cluster with single SSD per node. For shorter data we use, and for 25 to 40 gigabytes of data, we use the 8-node cluster with single hard disk per node. And here it is trying to show like 1 GB versus IP over IP, and then this is the new design. So here you can see that for 15 gigabyte sort, we are getting around 46% improvement. Okay, so it's the same InfiniBand network, but compared to the basic MapReduce design, when we are moving into the RDMA enabled MapReduce design, we are trying to get around 46% improvement. And then for 40 gigabyte sort, here we are getting around like 27%. So then the other benchmark which is used is called TeraSort, and we use this TeraSort, and again we try to use, because for different data sizes, again we try to also use increasing the larger cluster so that the data is much more balanced in like a scaling kind of thing. So here it is like a 30 gigabyte for 4 nodes, then 8 nodes, 60, 12 nodes, 100 gigabytes, and then 200 gigabytes for 24 nodes. And it also matters, again the memory also plays a role here. Okay, because we are trying to do RDMA from the memory, and how much memory you have per node, that also comes into the picture. So everything matters, like the network, memory, disk, whether hard disk or SSD. So all those things you need to take into account. And here it says like, so the cluster 4 and 8, so these have like 24 gigabytes of RAM each node, and these had like 12 gigabytes of RAM. And here we see like for 100 gigabyte sort, just comparing the IP over IP InfiniBand and this, we get around 41%. So then there is a, so these are like the standard ones. So now we started moving into the next one. So there is a Purdue people have put actually some workloads. This is called PUMA, Purdue MapReduce benchmark. So this is a kind of a new suite they have put, and this utilizes all different larger amount of data sizes, like 30 gigabytes, 80 gigabytes. So they are really going for these benchmarks of huge data. Okay, not just like 1 gigabyte, 2 gigabytes, because they can be cast kind of things at different levels. But once you go to 80, 100 kind of things, the really hard disk comes into the play. And they have also these benchmarks MapReduce with different kinds of things. So one is here the adjacency list, another is sequence count, self join. So these are some very fresh numbers we have taken, and these were run just on 4 nodes. We have not been able to run it on a larger scale node. So here we see just this like adjacency list MapReduce job for 30 gigabytes data, we are able to give you like a 24% improvement compared to the IP over IP. And here if you see, it's the same self join, but when the data size is only 30 gigabytes, we don't see any benefits. Okay, whereas the data size is more, so that means this is where really a lot of communication is happening to the disk over the networks. There only we see the benefits. Okay, so that is again the thing I want to bring it. When we are talking about big data, we really have to benchmark with huge amount of data. Okay, otherwise the numbers could be a little bit misleading. And here we saw almost like 52% improvement in this here you will see with this design. So now going to the Hbase, so similar kind of things we tried to do, but before we did the Hbase, we did a very systematic analysis saying where the time goes. We have not done that for the other components. That's what we plan to do. So here, what we did is like the Hbase, if you try to go through the code, you will see like there are different components, like where you are trying to do client serialization, client processing, server serialization, server processing, communication preparation, and then the actual communication. Okay. So what we try to do is over different networks, 1 gig, IP over IP, 10 gig, and our new design. So all these things, the different things, this is like the communication, client serialization, client processing, server serialization, server processing, communication preparation. So what we saw that is the communication that takes the maximum time. Okay, and this is where we try to put our new design so that we can reduce the communication time significantly. This is for Hbase put operation, and this is the Hbase get operation, so that we can get the maximum benefit. And here we see almost like a factor of 6 improvement over 10 gig for the Hbase put, and then also for Hbase get around like the six times improvement. So the way that then we design this is again, the figure is very similar to the previous one. So we take only the Hbase, the get and put operations, and then try to modify that code with our new design, and all other parts go through the sockets. Okay. And these are some other additional numbers, like again Hbase, there are different modes you evaluate. This is trying to show like a single server multi-client request. So this is the latency, and this is the throughput. So this is the lower is better, this is the higher is better. So here the charts which are being shown, like this is the 1 gig, this is the black line, then IP over IP, then 10 gig is this blue line, and then this is the new RDMA design. Okay. So here you can again see that for Hbase gate, for 4 clients and 16 clients or gate throughput, we are around getting around 27% improvement for 16 clients with over 10 gig. Now this is the same YCSB benchmark which I showed earlier, but now we are trying to run it on the Hbase with the new RDMA average design. Okay, just to see how well this is going to help here. So here the same thing is like the read latency, and the number of clients are increasing here, 8 to 128. This is in the time, and this is the write latency, the number of clients up to 128. And here we see for the gate latency, if you take like this is the line with the new design, the red, and then the red here. Here we get around, like compared to IP over IP for 128 clients at this point, we get around 42% improvement, and here we get around, for the gate we get around 40%. So these are the individual components, and then recently we tried to put them together. Okay, because as we saw, like in the Hadoop, HDFS is the lowest layer. So HDFS itself can give some benefits, and let's say the Hbase itself can give benefits. How about if we put them together? Like both uses the new design, can we get better benefits? And that's what we did the study here. So this chart is trying to show that. So it is an integrated design, the RDMA design for both HDFS and Hbase. And the numbers are trying to, what is trying to be shown here, like there are 4 bars here. So this is the gig number. This is the IP over IP. So that means this is everything is running over sockets over gig, everything is running over sockets over InfiniBand. And here, this pink line is the HDFS is the new design, but the Hbase is running with the old design, like the sockets, the default sockets. And then the red line is both of them are RDMA. Okay, so that's the kind of the 4 bars which are trying to show here. And these numbers are with 4 region servers with 100% update. So this is the put latency. Here is the latency, and this is the throughput. And here we see, like almost compared to the IP over IP here, we get around 37% improvement, and over the HDFS-IB design itself, we get around 18%. So if you see here, like the red line is always like even coming better than the pink line. So that means what it is trying to show that, yeah, you can have each of these components have design, and then when they put them together, you get the additive effect, and that's what it's coming from. So that means once we have all these components being completely redesigned, and when you put it together, the entire Hadoop framework, people will be able to extract more and more benefits. benefits. So let me spend a little bit more time on the Memcached, which is a little bit different component which comes from the Web 2.0. So here again, what we try to do is like we had typically the clients have been using sockets, and we designed also the RDMA client. Not only we handled on the server side, we also had to do RDMA client. So typically there are like master thread, there are sockets worker thread. So we introduce some verbs worker thread, so they can coexist. Okay, so that even the sockets call can come, or RDMA client can send also the calls, and we should be able to, if the RDMA client is calling, then we handle that through the verbs worker thread. And in all our design, even in the earlier one, including this Memcached also, we try to keep the API the same. Okay, so that any application which has been written with HDFS or MapReduce or anything, they don't have to change anything. They just use our new library or the middleware. The same thing happens also on the Memcached. And so the numbers I'll be trying to show here this is the evaluation with Memcached server 1.4.9, Memcached client 0.52. And here we try to do the studies here. We also included SDP stack also. This was a little bit earlier study, so we used SDP. So there are multiple lines. So this is like a 1 gig line, the black one. This is the IB over IB line. This is the SDP line. The green one is the 10 gig. And then we have the new OSU design. And OSU design, we had two different variations. Yesterday I indicated InfiniBand provides two kinds of transports, in fact multiple transports. One is the RC, reliable connection, and the other one is the unreliable datagram. So we tried to explore both and then combine with a hybrid approach. I mentioned for our MKI stack also we use that hybrid to provide scalability. So similar designs we have taken here. And here we see like the Memcached like for 4 bytes. So this is actually a DDR cluster, this is a QDR cluster. And here we see like almost in the end factor of 4 improvement over the 10 gig tone for 2 kilobytes on this DDR cluster. And with respect to transactions per second, because this is like the Memcached, people are also interested like how many transactions you can handle per second, not just the reducing the latency, but the system will be able to handle more transactions. And here we see like for short ones, the number of clients 4 and 8. So if you see here, like these are SDP, IP over IP, GG, but these two designs, like the RDMA enabled designs, they just give significant amount of TPS. Like we go up to like 1.3 millions per second here, and then we also try to scale the number of clients up to 1024 clients. And here we see very interesting thing. These are multi-core platforms, so now the number of cores also comes into play. So these are like 8 cores, so up to 8 clients you can handle very easily. So that's why we see the numbers rising very top very quickly. But then after that it comes down, because when the requests are going to the outside of a node, you cannot sustain. If you have cores, if you have nodes with more number of cores, you should be able to still see this rise. But overall also we try to give here like a transactions which is around like a 650, I think this is the 650 thousands transactions per second we can give here. So then in the Memcached there is another benchmark called Olio, which is an open benchmarks again, and we try to use that. And a similar kind of things we see here. There is a big difference between like a SDP, IP over IP versus the new designs. Here we see around up to 8 clients, we see 4 times better. And as here we try to scale it to larger one. That's why we brought the hybrid into play. So that this is our new hybrid design, which tries to perform equal or better than the UD or RC, just like our MPI design. That hybrid car example I gave yesterday, the similar kind of design we can have here, so that it scales with reduced memory footprint. So then we worked, I have a student who works with Yahoo, so we worked with them. He tried to mimic, of course we cannot use their direct benchmarks, those are very proprietary. So we tried to mimic their ads benchmark, whatever they use internally for generating the ads, revenues kind of thing. So we tried to convert that into a synthetic benchmark here. So here again the similar kind of things. If you see, this is like the SDP and then IPO and IB. So these are our new designs. So here we see just even with 8 clients, we can deliver almost 12 times better performance compared to the IPO and IB. And then and on the right hand side, we are trying to show on the same hybrid design achieves the comparable performance to that of RCS. So with this, let me conclude this. So these are all our initial studies. As I said, like the broad picture is huge. Okay, I mean it's just like starting, and people are trying to explore, and this is where we have done some initial studies. And from this picture, we have just focused on only just two of these parts, point-to-point and a little bit of IO and file system, but all these other issues need to be investigated. But more importantly, this is what we need, like some operable changes, because as we make the networks faster or network components faster, the bottleneck shifts to some other place, and then that's what we need to take a look at it the next time, so that we can actually get the complete benefit of both the stuff. So with this, let me conclude here. So what I try to present here some initial designs to take advantage of the InfiniBand-RDMA for different components, the HDFS, MapReduce, Hbase, and also Memcached. So these results are promising, but the main thing, we are now working on some integrated designs of all these components, and at the same time trying to go into much more details of the benchmarks and running the applications, trying to study all these interplay between the components. I said the memory, the number of cores, SSD, hard disk, to see how realistically the designs can benefit. And also there are many other open issues need to be solved, including the design timeless changes at the upper layer. And if we can resolve this, and I think it will take several years for not only us, might be the other people in the community who will be working on similar things, trying to come up with the best possible solution. So then only we can see that it will enable the big data community to take advantage of all the modern clusters and the Hadoop middleware to really carry out their analytics in a faster scale. Okay. So with this, I will just stop. Some of these are our pointers, and I'll be happy to take any questions. We have a few minutes.